All right, so in this video, we will be talking about the analog to digital converter, or we can call it the ADC or A to D converter. Okay, it's one of the peripherals that already exist on the PIC18F, and some microcontrollers have it, others don't. All right, so let's get started. So why do we care about analog to digital converters? And the answer is because the world around us is actually analog, and we usually will be able to capture it with analog sensors. But in order for us to deal with it in a digital system like the microcontroller or any microprocessor for that, or any digital computing device for that matters, we need to digitize it, and that's what the purpose of this module is. So generally speaking, you will end up with some sort of a sensor that gives you an analog output. Here are a few examples of these sensors that I found online. There are many more. But generally speaking, I like to think about them, at least me, myself, I like to think about them as a couple of things, or a couple of types. So the first type actually outputs an analog voltage. So one of them is an analog temperature sensor. This is the part number. There's an IR or infrared distance sensor, amplified microphone. So they already generate analog voltage, and all we have to do is just take the analog voltage and figure out a way to move it into digital numbers. The other one, which we'll be dealing with exclusively today, is sensors that act as variable resistors. We're going to see that there's a photoresistor. You already see it on the board in here. That's a photoresistor that I just looked around the house and or in my electronics parts, and I found it. You might not have it. If you have any of the other sensors, the same methods and the same approaches I'm going to teach you today work with these types of sensors. There are force sensitive sensors. The idea behind all of these sensors is like whenever you do something, the internal resistance actually change, and we'll be able to measure not the resistance but the voltage drop across it, and that's how the ADC will do it. I'll walk you through how to do it today. Okay, so if you have any of these sensors or any other analog sensor, just figure out whether it's a variable resistor or is it just output some sort of voltage, and figure out how to use it. All right, so okay, so we know that, and just a quick note in here, this makes sensors. It's actually for hobbyists, but it's a good reference for all sorts of sensors. So if you're interested in measuring certain things, maybe I would refer to that book. All right, so let's get started. So what I want to talk about is a little bit about digital versus analog. So if you have taken any signals and systems or discrete signals and systems, you already have seen this concept. So if you haven't, you will see it in our department. We actually you will see it in our department because this is just another thing you need to know as an electrical or computer engineer. But generally speaking, I'm just going to introduce you to it just in case you haven't heard of it or you haven't seen it yet. Digital versus analog. So the world around us is analog, and what we deal with so far in this course, we've dealt with only digital signals. And what I mean by digital signals is something we called it as a 1 and 0, 1 and 0, 1 and 0. And frankly speaking, these 1s and 0s are just 0 volt or 5 volts. Some different technologies in digital, that 5 volt might not be 5, might be 3.3 or something like that. But generally speaking, you have a couple of voltages. One you consider high, the other you consider low, with a little bit of tolerances. So if you get 4.9, you're going to consider the 1. On the other hand, in the analog world, like for example, this here, I'm showing you a cosine wave. That wave can take any value between 0 and the maximum here you can see is 5, any value in between them. So it could be 2.5, 2.3. There are infinite number of values in here. So the computers or the microcontrollers actually deals with 1s and 0s, as you know, not with analog signals. So our purpose today is actually to convert something like this to digital signals. Not necessarily to 1s and 0s like this, but to a number. Okay, so let me walk you through it. So generally speaking, you can spend really a really long time studying analog to digital converters. Actually, there are some people that spend their career just designing and working with ADCs. For today, for sake of simplicity, we're just going to focus on, or we're going to just simplify the concepts of ADC into two things. We have sampling and we have quantization. And the process of sampling is, I'm going to give you an example here. I have this blue signal here, which is an analog signal. And what I'm going to do is that I'm going to sample it in time. So I'm going to periodically and consistently just try to read its value at certain points in time. So for example, I can read it here, 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 and at each point, I'll get a voltage reading. Okay, so this way, after I do that, technically speaking, whatever is in between two sampling point is kind of lost for me. So I don't know that there's a bump in here. So if I'm to reconstruct this signal, roughly, I'll be basically just connecting these points in here together with straight lines. So I might not see this dip, but I will see the average. All right, so there's this is sampling, this discretized. It did not make the signal digital yet, because the value it takes at each point can be of infinite amount as well. The amplitude could be any number. In this particular example is between -1 volt to 1 volt, any number in between, any float number. There are infinite numbers that it can take, or infinite values. But the outcomes of this sampling process is just a bunch of numbers. Let's for now consider them any value. These numbers can take any values, but I discretized it in time. Okay, there are rules of how fast or how slow I should be sampling the signal. If you know it already, we call it the Nyquist frequency, and the Nyquist frequency tells you that you need to sample at least at a double the frequency of the signal you're trying to capture. If you did not understand what this is, it's just basically a rule of thumb that to help me sample a signal, and if I want to reconstruct it into analog, I will be able to. So for example, this might not be as good, but I don't know, I'll have to figure out what the frequency is. But anyway, for our purposes, we're not going to be definitely dealing with signals that change periodically or do something with signals. We're just going to measure voltages, analog voltages, or analog signals, saying this is not as important, at least not on this microcontrollers. So other microcontrollers are dedicated for signal processing, and you can do voice or sound processing on it or whatnot. That will become more important. But the concept is the same. You do have some sort of a sampling frequency or sampling period, okay? All right, so the process of sampling, again, is just discretizing that signal in terms of time. So I'll get a bunch of numbers, a sequence of numbers. However, because we're dealing with digital systems, I can't store infinite numbers. As you might know, I'll have storage limits. For example, depending how many bits I have, in an 8-bit system, I can only store 256 numbers. And a little bit more, for example, you probably have heard in programming that we use 16-bit integers so that we have more numbers to store. Okay, so there are certain limitations. And in terms of sampling and or in ADC, we talk about quantization, meaning, so this value here can take any number between -1 and 1, but frankly speaking, it might fall, let's say this particular, let's say this value in here. Okay, so if I'm to sample this value exactly in time, so it will be that particular point in here, not where the end of the red line is, but this very, very particular point. And if you think about it, if I only have a limited number of values or digits that I can actually assign to it, this one here did not really align to this value or this value. So I'm gonna have to approximate it by saying, well, I divided the -1 to 1 to a bunch of numbers, 1, 2, 3, 4, 5, 6, 7, 8, let's say just 8 numbers or whatnot. Okay, so I'm gonna have to assign it to one of these numbers. So I'm gonna either round it down or round it up. And the process of just assigning digital numbers to the actual values of the sample is what we call a quantization. And this process actually introduces certain errors, but that's okay for our purposes again. And the more numbers we can actually assign, or the more quantization levels I can actually, or quantization steps I have, the more accurate my approximation will be. Okay, and the thing that defines how many levels I can actually split this into is the number of bits of the ADC. All right. Okay, so to recap, what I have is I have a couple of things. I need to sample in time, so I need to do now, and I need to sample in terms of amplitude. So if I do, or quantize in terms of amplitude. Once I do this, I'll end up with a bunch of numbers, and these numbers are exactly what I'm looking for, and that's the output of the ADC, as we're going to see shortly. Okay. So resolution. So I'm going to talk a little bit about resolution now. So I took this signal and I told you, well, we define it into 8 or 10 steps. But what we're going to be seeing is in this particular microcontroller, the ADC, the internal ADC that it has actually 10 bits. Okay, so it's a 10 bits microcontroller, ADC, sorry. Whenever you go and buy an ADC, one of the most prominent feature you're going to see, it's going to tell you the number of bits it can handle, or the number of bits it can output. So this one is a 10-bit ADC. Some of them are very expensive and they can get 16 bits ADC because you're going to have more resolution. So what's a resolution? Well, a resolution is the smallest step that I can actually discretize this value to. So I have a number between 0 and 5, okay? And in order for me to know what is the value between here and here, I need to figure out the resolution. And the resolution can be figured out just using this equation. I'm going to take the maximum voltage I have. In my case, it's going to be 5 volts. It can be something else if you choose to, but let's stick to 5 volts. And the minimum voltage I have, which is 0, and then I'm going to divide it by how many levels I have. And the number of levels are defined by 2 to the number of bits. So in our example, what we have is we have 5 volts minus 0, and I have, because my ADC is 10 bits, that means I have 1024 levels. So 5 volts in general, so between here and here, I have 5 volts. I'm going to divide them into 1024 levels. That means the difference between these levels is 4.8 millivolt. So what this means is the lower resolution I get, or the lower change I can actually see, has to be greater than 4.88 millivolt. So if I have a change that is between these two numbers, which is basically 3 millivolt or something, I will not be able to see it. And that's what the resolution is. Okay, of course, if I increase that 5 volts to 10 volts, the resolution is just going to decrease. I'm gonna not be able to be sensitive to 4.8 millivolts, maybe a little bit, maybe it's actually double that. It's going to be 8 point something millivolt. Okay. All right, so the number of bits tells me how many levels I need to split between between the maximum and the minimum. And we're going to see that these numbers here, the maximum and the minimum, are software selectable on this microcontroller. You can tell it what you want to do, or what is the high, what's the low value. However, you cannot change the resolution, which is the number of bits. This is why I'm saying the ADC usually is assigned, the name of the ADC tells you it's an 8-bit ADC or a 10-bit ADC or a 12-bit ADC or something, because generally speaking, it's usually fixed. You might be able to operate it in a couple of values, but the maximum values is what's advertised. So in here, we have a 10-bit ADC. You can, technically speaking, you can hack your way around it and operate it as an 8-bit, but we're not going to do that today. All right. And if you have it as an 8-bit, that means I'm dividing that 5 volts into not 1024, but to 256. So my resolution is going to get reduced. All right. To sum up, I will have an analog signal like this, or an analog voltage, and I'll be sampling in time and in value. And what I want you to think about it is the following. So I will be having bunch of numbers coming to the microcontroller from the ADC, and these numbers are digital, and they represent the value of this red line at a certain time. Okay, so I'm gonna get that value, this is the number it gets, I'm gonna get that value, and I'm gonna get a number, and each one of these numbers is gonna be 10 bits. Okay, all right. So, okay, well, the ADC, of course, has to be external. So, the microcontroller is a sort of a complete digital device. It has some analog and components, all the components inside it are analog, but the whole system is digital. But it has some sort of analog capabilities as well inside. But anyway, it exposes some analog pins outside. And what I mean by analog pins, it's analog input. So we're converting from analog to digital. This particular microcontroller does not convert on the opposite direction. So if you have something digital produced by the microcontroller and you want to output it to some sort of an analog device, it does not do it. There are ways on another peripheral that will help us deal with some sort of analog devices. But for today, what we're going to deal with is I have some sort of an analog output, and I'm trying to actually get into the microcontroller, and so that I can do something useful with that number. And those analog inputs to the microcontrollers are actually AN0, 1, 2, 3, well, AN2 and 3, and then you get AN4, AN5, 6, and 7. These AN stands for analog, and I do have about 13 of them. Okay, so I have 13 analog inputs. I can have 13 different analog channels interface with this microcontroller, which is kind of a lot actually. Today we're gonna learn how to do one of them, and then towards the end I'm gonna teach you how to use 2 of them if you needed to. All right, so this microcontroller might have all these 13 bits or 13 pins to the outside world. However, it only has one ADC internally, and I'll show you what this means in a minute. Okay, but it only has one module that can convert these signals. All right, So we move on how to use it. We know that we need to interface with the AN0 and whatnot, and you can see it on here on the chip. I'm gonna show you a couple of circuits. So I already rewired everything, but you can see I will be only using the AN0 and AN1 for today. Okay, we're gonna start with the AN0, which is this wire here, and I'm gonna show you what I'm doing here. All right. Okay. So, well, an ADC is just a peripheral, and like what we saw in this microcontroller, most of the things we deal with, or if we want to control anything, we just basically modify some bunch of register. And the main registers that we're going to be interacting with are the AD result high register and the AD result low register. And if you guys remember, the ADC is 10 bits, but my registers are 8 bits. I can't fit 10 bits and 8 bits, so I need two registers to do that. And what we're going to see is, yes, we have two registers. That means we have 16 bits, but we're going to be just using 10 bits of them. Okay, and we're going to see, basically what I'm saying is the numbers that the ADC will output will be stored in these two registers, and we're going to read them from these two registers. So I'm going to get 8-bit in one and 2 bits in the other, and I can choose which one is which. The other three ADC control registers, I have ADCON 0, ADCON 1, and ADCON 2. We have seen, and I've written many codes saying AD converter 1. And my purpose was, and you guys saw my comments, is probably like, oh, turn off the ADC. I wasn't necessarily turning off the ADC. I was just telling it, do not use these inputs that are highlighted in red as analog, just use them as digital. Okay, so we're gonna see these control registers and what they do. These comments here, they help me figure out what each one of them does. It's kind of confusing to remember which one is which. I usually open all these slides or the data sheet. These slides are directly imported from the data sheet. They're just a little bit more organized. Well, they're differently organized. Okay, so the port pins, we know what this does. It's mostly decide whether a pin is a digital or analog. An ADC operation, we're going to see what I mean by that shortly, and then clock and justification. So let's go through these registers. There's many of them again. These just store the results, so there's nothing that I need. Basically, it samples something and stores it continuously. All I have to do in my code is continuously read these values to figure out what the outside world is, or what the value of the voltage in the outside of the microcontroller is. All right, so let's talk very briefly about these control registers, and then I'm gonna go back and write some code and show you what they are. So ADCON 0, okay, so what we have is we have basically three parts to it. The first part, which is here, okay, so I have CHS, or it stands for Analog Channel Select. Remember, I have 13 channels, or 13 pins connected to the outside world. Okay, so technically I can use 13 analog input to this microcontroller. I haven't had the chance or the need to do this before in any microcontroller, but this microcontroller does allow us to do this. But in order for us to do this, we need to figure out what channel we're dealing with. And the reason why I need to choose a channel, let me scroll a little bit faster, is the following. Again, the microcontroller here has only one ADC converter, one only. It interfaces with 13, but it only have one. And it turns out to be that it can only convert one at a time. You cannot convert 13 channels all at the same time. What you can do is you can choose one of them and convert it. So that number, or these values here, which are CH0, CH1, CH2, CH3, are basically what will select which channel is being converted. Okay, so let me go back in here. So you're going to see that these are the CHS 0 to 3, and you can see that here. What this is technically a multiplexer. It's not a digital multiplexer, it's an analog multiplexer. So what I will be doing is I'll be connecting certain pins here, okay, to the outside world, and let's assume that I connected all these outputs to analog signals. The CHS will connect one of these switches and will route the analog input from the outside world into the internal ADC converter. Okay, so again, that's an analog multiplexer because the signals that come in here is analog, and the signal that comes out is analog too, but it operates in the same way as a multiplexer does. Okay, and we're going to see that if I have more than one ADC or more than one signal that I want to interface with, I have to do them sequentially. So I convert, for example, the 0, and then I open that switch and I close that switch and I convert that, and so forth. So whenever you read the output of the ADC, the digital, you need to figure out what did I convert? Did I convert 0, 1, or 2, or 3? And I'm going to show you how to do it with 0 and 1, but the concept can be expanded to all of them. And in addition, you're going to see, there you go, we'll come back in here. Well, I'll come back to that slide again. But anyway, so we get the channel here. This is the channel select. This is what this does. So you're going to see initially I'm going to set it to 0. That means because I'm going to just deal with A and 0 only. But if I need more, I can change them. And I can change them on the fly, so while my program is running. All right, so the other two signals are not very difficult to understand. So for example, the go and done, or let's start with the add on. Okay, that add on is just an ADC on or off. This is what turns off or on that ADC. If I really wanted it off, I should have just put a 0 in that particular pin, and I would have just basically made it completely off. Whether I chose these pins to be analog in or out or whatnot, like for example, if I want to preserve some power, I can just physically just turn it off. We're gonna just keep it on. Today we're just gonna keep it on because we're gonna be using it continuously. Go and done, it can be used for two purposes. The purpose for go is actually when you actually set it to 1, you're telling it go and convert. Okay, so every single time you have you want to acquire a sample, you tell the ADC convert. This is basically these red lines in here what I have. So you're going to tell it convert. It's going to take its time, it's converted, and it will tell you an output, and then it will stop and tell you, okay, do you want me to convert again? And every single time you're going to say go and go and go and go and go. That's what we're going to be doing. Okay, so every single time we're going to tell it go and convert, go and convert. While it's converting, it usually takes some time. I can read that signal. Okay, as long as it's 1, because it's going, it's actually working internally and converting that particular sample. I cannot do anything with that ADC. I have to wait for it to finish, or if I stop it, the value that I'm going to get out of it is not right. So once I read it as a 0, that means it's done. I know that it's done converting, and the value that I have in the registers, ADRES, H, and whatnot, these two is a valid input. All right. I'm going to show you how to use all of these in shortly in a code. All right, so then ADCON1, we have used this and we have set it to 0F or FF. This is what I use these interchangeably in my code. And what this does is, let's focus on the PCG, whatever it stands for, Port Configuration Control Bit. Okay, these are these 1, 2, 3, and 4. Okay, so those 4 bits, what I set to F, when I set it to F, meaning I put 1, 1, 1, 1. And if you see that table, it tells you 1, 1, 1, 1. That means you're doing all of these as digital inputs. If you want any of these inputs to be analog, you're going to have to come back to this table and say, well, for example, today we're going to see the AN 0. I need this to be analog and the rest to be digital. So I need to fill these with this particular number, which is an E. If I want later on, we're going to see AN 0 and AN 1. I need this as an analog. This is as an analog. So I'm going to put that number in these particular 4 bits. This just tells me whether I'm dealing with the input pin as analog or digital. I'm specifically saying whatever I want. So the upper 2 bits in here, it turns out to be that I can select my voltage reference. The ones in that equation in here, I showed you that voltage references were 5 and 0. As it turns out that I actually can select what values I need here. Okay, so if I put both of them to 0, that means I'm saying, well, the voltage reference configuration bit for the for the negative, sorry, the VG1 is the negative here. Okay, that's basically the 0. If you put it to 0, you're going to use VSS, which is connected to 0 in this case. If you choose the VGF, the VC, whatever this is, VCFG0 to 0, okay, you're basically telling me use the positive sign or the 5 volts in here. If you have something else and you want to choose it, you can. However, you're going to have to use these AN2 and AN3. So let me go back to the pin graph here. So the pin graph here, it turns out to be the AN2 and AN3. You can use it as channels, as input, or you can use them instead of the 0 and 5 if you want some external references. So you want the 0 here, the maximum and the minimum, you want them to be external to the microcontroller, not necessarily 0 and 5. You have the option to do this, and they can be basically negative voltages or high voltages depending on your application. For simplicity for today, so that we don't actually complicate the circuit, we're just going to use the internal power, basically 0 and 5. It's as if I connected this to 0 and this to 5. I can choose whatever I want. But if I chose to do that, I need to do a couple of things. First, I need to make sure the AN2 and AN3 are actually analog, so I need at least this particular value in here. That means I'm dealing with AN0 and AN1 as analog inputs too. So something to keep in mind. And here I'm going to have to put them as 1 and 1. Okay. Of course, I can choose one of them, not the other, and whatnot, and you get the idea. All right. So going back to this graph, you're going to see that this is what they are connecting in here. So this is AN2 and AN3, and it's telling me where is my V reference plus and minus, and the plus is the maximum, and minus is the minimum. you can see this graph slowly, and you can see it's not, this is another multiplexer here, an analog multiplexer. All right, so we have ADCON 0 done. It's like mainly it selects the channel, turns on the ADC, and tells it to go and convert, or I can check it as a status bit, whether it's finished converting a certain bit. Here, it's just telling me what pin is it an analog or digital, and the other two is just telling me the reference voltages. All right, so the last of the ADC control registers actually controls clock source, acquisition time, and justification, okay? There are actually three, well, two of them are related, the other one is not. So let's discuss them one by one. I'm gonna start with the simpler of them, which is the ADFM. Okay, so the AD is result format select bit. What it tells me, it's right justified or left justified, whether I put 1 or 0. So let me show you what do I mean by right justified. Remember, the result I have is a 10-bit result. Okay, so it's a 10-bit result and I'm storing it into 8-bit registers. So it turns out that I can justify it to the right or justify it to the left. So if it's right justified, meaning I'm using the address low, the low byte basically from 0 to 8, I'm using all of them and I'm using 2 pins from the higher one. So what I'm doing is basically my actual data, the 10 bits, is right justified. Think about it as you do with Word or any word processing software. You actually click right justify and basically you're aligning it to the right. And that's what I'm doing. The left justified is simply just basically I'm using the 10 bits, but the 10 bits are the lowest two significant bits are 6 and 7 from the low, and from 0 to 8 I have the higher significant bits. All right, so you can choose whether you want to do it or not. I think today in my code probably I use the right justified, but you can choose to do something else if you choose to. It's up to you to do wherever you want. All right, so this is a justification bit. So then this is not implemented. Then what I have is I have a couple of things in here. So the first one is, let's talk about this here is acquisition time select bit. Okay, so we have 0, 1, and 2. This is the acquisition time, these 3 bits in here. And I have a few values in here. So let me explain what this means. Acquisition time is the time between capturing an output signal. Okay. Let me rephrase this. So you have an analog output coming into the microcontroller and you want to basically convert it into digital. So what happens is it turns out that you need to really read that for a little bit of time. You need to keep sampling, or not sampling, you need to keep reading that voltage for a certain amount of time before you start the conversion, so that you get all the analog components. There's a capacitor internally that needs to be charged. And in order for it to be charged, remember capacitors are slow, so it takes some time. So that time is what we call an acquisition time. And again, the acquisition time is the time between an analog signal going into the ADC to be converted and the time it actually gets converted, or the ADC works on it to be converted. All right, so let me show it to you on a slide in here. So what we're going to be seeing is a couple of things. So we're going to tell it, hey, ADC, please do convert some sort of a value from the outside world. So I'm going to issue the go command. In the go, I'm going to have something we call an acquisition time, okay? Forget about automatic for now, but an acquisition time is the time that it will keep reading that analog voltage till some sort of an internal capacitor gets charged. Okay, that internal capacitor, once it gets charged, my value from the outside world has been stored in that capacitor. You can think about it this way. And now I can start my conversion because that value is not gonna change. So what I do is I'm gonna be reading the outside voltage for an acquisition time, and then I'm gonna flip some sort of a switch so that I disconnect from the outside world. So my capacitor stores that value. The value is still, it's a capacitor, so the voltage across it is analog, and then I'm going to convert it into digital. And as it turns out that this particular microcontroller, what it does, it converts each bit with a certain amount of time, and that time is TAD. Okay, so TAD stands for the time, let me just read it for you. The basically stands for, I always forget what it stands for. It's the AD conversion time per bit. Okay, so per bit, what is the analog to digital conversion? So this will take these are basically the bits, the 10 bits. So this will take TAD, this will take TAD, this will take TAD, this will take TAD, and so forth. You need some extra ones in here so that it actually starts the process. I need some extra one to discharge that capacitor so you can actually read again. Okay? All right. So going back in here, what we care about is the following. We can actually, this particular microcontroller allows us to choose the acquisition time. Okay, so the acquisition time I have in here, it allows us to choose how long do I want this acquisition time. And if you go read the microcontroller data sheet, you're going to see that this can get a little bit on the complicated side, and you can actually go and compute it manually, figure out the voltage values and the capacitor values and the temperature and whatnot. There's actually a lot of calculations involved. Or you can just do it automatically, and automatically is just the multiples of the analog to digital conversion per bit, which is the TAD, this one here. All right, so if you set it to 000, that means you will be actually doing it manually, and you're going to actually introduce certain delays in your code so that you guarantee that this acquisition time is a certain time. We will not do this. It's a little bit more complicated, and it's not very necessary, at least not for our purpose and for our application. What we will be doing is we're doing some sort of an automatic. This is why this one here, it's saying automatic acquisition time, because this is what we're going to be using. What we'll be using is we're going to say, okay, what is the TAD here, which is basically the time you need to convert one bit. Okay, so this is one bit. So again, every bit will be converted. It'll take some time. So you need about 11 bits because I have a 10 bits total. You have like basically 10 bits here and another bit to do the conversion. All right, so what we're going to be doing is we're going to do multiples of these, and as it turns out to be that you can actually say two of them, basically as if it's the time that needs to convert 2 bits, time to needed to convert 4 bits, 6 bits, 8 bits, and so forth. All right, so how do I choose this? Well, it depends on the TAD, and the TAD is decided by the conversion clock. But before I actually talk about the conversion clock, let me show you, as it turns out to be, well, let's talk about the conversion clock. The conversion clock, the ADC conversion clock, is what will allow us to figure out what the TAD is. All right, so the conversion clock will allow us to figure out what that TAD is. And as it turns out that you need, well, we're doing something continuously in time, 1, 2, 3. You can see that I really need a clock, and I can actually choose that clock. So for example, I can choose the oscillator, the internal oscillator that I have, that I'm operating the whole microcontroller from. And this is the FOSC, the one we talked about before, which we have considered to be 1 megahertz. Okay, so but we don't usually use the 1 megahertz itself. What we do, we slow it down a little bit. So it's either we divide it by 2, 8, 32, 4, 16, 64, and so forth. And the ADC itself has an RC oscillator. For example, if you want to turn off that oscillator because it's in sleep mode or something, we're not doing that here, but if you care about power, you need to figure out what portion of the microcontroller to turn off or whatnot. You can actually, it turns out that it has an internal oscillator, an RC oscillator, and you can choose it in here, okay? You're going to see, well, okay, so there's a couple of things that we need to choose. We need to choose how many TADs do I need, and we need to choose the oscillator clock, okay? And this can actually, depending on the data sheet you read and whatnot, you're going to see that there's a table usually that tells you, okay, let's think about it this way. So TTOC is actually the opposite of that. So this is the FOC, this is the frequency. Okay, if we're talking about the T, which is the period, you just basically, instead of dividing by 2, we're going to multiply by 2. So for some reason, they wrote the table this way. All right, so it tells me that, okay, if you choose 2 or 4 or 8 or 16 or 32 or that, or the internal RC oscillator, this is what you're going to have to choose, okay, as time, as here, basically what you choose in here. All right, but what I really more care about is, okay, what is the maximum device frequency so that you get an appropriate TAD? As it turns out to be that TAD has a certain properties, and you can read it in the data sheet. If I remember correctly, well, it's written here actually. You need about 1.7 microsecond or something. I forgot that particular number, but you need a specific number so that conversion here, you have enough time to convert 1 bit. All right, so what we have is maximum device. So these choices will affect my maximum device frequency. So if I choose the 2 TOCs, okay, because this is one of the fastest, okay, this is one of the fastest because my frequency is only being divided by 2, my sampling. It's not by 8 or 32. So if I'm operating at 1 megahertz, that means the clock I'm using to operate the ADC is 500, well, 1 megahertz, that means half a megahertz, okay, or 500 kilohertz. 500 kilohertz, that means I can capture pretty fast signals. So the slower I go, the slower the sampling that I do. Anyway, if you've taken signals and systems before, this relate to the Nyquist frequency, okay, and the fastest frequency I can sample. But because we're not doing actual signal processing here, all I want you to know is that affects the maximum device frequency you're operating on. And because we're operating on 1 megahertz, this is the maximum. So if you're operating at lower one, that's fine. So this one here, the maximum device frequency is 1, 5, 11, 14, and so forth. All of them are actually meet the ORG standard because we're going to actually operate at 1 megahertz. But if we're operating at 80 or 40 or whatever other megahertz, you're going to have to actually take a look at this table. Okay, to summarize, I know I talked about a little bit about it, and it gets really complicated, and you can read it in the datasheet if you choose to, or if you're interested in it. To summarize, what you need to do is you need to tell me how much is the acquisition time, basically the time before you do a conversion, the time you need to actually keep reading the analog signal, and I'm gonna do it just automatically as multiples of TAD. Okay, and the TAD is usually chosen by figuring out what frequency I care about. You're going to see today what I will be doing is I'll choose the 2 TAD because that's the fastest, okay? And I will also choose, I believe, the 00, just a half of it. So I'm going to just set these, and I'm not going to change them. I can change them by software if I choose to, but these are the two values we're going to stick to today. All right, so 3 control registers for the ADC. We're going to see that in code and how it actually affects us. All right, so what next? Well, how do I do these conversion? Okay, so I talked a little bit about it now. So let's talk a little bit more practical now. How do I actually do a conversion? Well, we have a bunch of steps. I'm not going to go through it now. I'm going to go through them in the code because we're gonna add code under each one of them. But these are the general steps. The reason why I'm jumping back and forth between the slides is because I organize the slides in such a way that you get the add con, like basically the registers right after each other, so that you don't have to go scroll up and down. Because I find it very useful when I'm coding to go back, like, what do I want? The AD con 0. Okay, here it is. AD con 1 is here. AD con 2 is here. Okay, but anyway, this is why they're organized this way, and I will follow these steps to actually program everything. But before I do, let's do that. ADC, let's do this. Okay, so these are the conversion steps. We'll get to that when I'll talk about code. I just want to tell you that we're actually going to be dealing with the ADC is a peripheral, so it can operate as interrupt or pulled I/O. Because it's an interrupt, if you guys remember the control registers, we dealt with RCon and INTCon 2 and 3, but I grayed out these because I told you they're related to peripherals. As it turns out to be that the ADC is a peripheral, so we're going to be dealing with these particular registers, and I'll talk about it. Basically, one has the enable, one has the flag, one has the priority. I don't know which one is which. I think, okay, they're here. Okay, you don't need to remember which one is which. All you have to do is just go in here. And I found this table is also useful. These are all the registers that the ADC interact with. For example, if I want the ADIF, which is the flag, if I'm using the interrupt, I know that it exists in here. If I need the ADCon 0, for example, I know that the CHS is here, something. Okay, so these are just all the registers with that explanation. I find it like once you get used to it and you figure out what is the meaning of each one of these signals, this table just, you can read it here and you can just basically it'll help you code faster. Okay, so let's get started. What I want to start with is I want to start in the following. So before I actually go and do a sensor and whatnot, you want to test everything simply. So what I'm going to do is I'm going to say my analog input is going to be provided by some sort of a potentiometer. And frankly speaking, what I'm doing is a voltage division, and that voltage divider is changing based on the value that I put on this this particular potentiometer. So what you're going to see is this particular potentiometer currently is connected to ground at the bottom, to 5 volts at the top, and I think they call it the wipe. It's actually connected to AN0, which is the input. So when I change it, what I'm effectively doing is I'm taking part of that 5 volts. So when I'm changing it, I can go all the way from 5 volts all the way down to 0 volts. So this is just a basic voltage division. I find it just easier because I want to see how to write code, and then we'll modify it and do something else with it. All right, so let's get started with the code. So what I did is I get started by putting the main C here, and you can see that I'm using the LCD because I find it a little bit easier to just so that you get to see the numbers. So I'm going to be using the LCD. So I already imported my liquid crystal C and liquid crystal H. Okay, so we're going to do that. And what I did is I went to that slide, the one here, and I copied these numbers and I put them as comment so that we get to see them one by one. They're exactly the same. I just removed, I believe I removed the which register does what. But anyway, so let's get started with it. So what this tells me is you need to configure the ADC. All right, so it needs to configure the ADC. But before I do, I forgot that, well, I have the LCD, so I need to set it up a little bit. So the LCD tells me, well, and you can see that I'm going to share code that is commented already so that you can actually read it. So I will have the try SC. Okay, so as it turns out that I connected the data pins to port C, actually, okay, not port B, but port C. I think I connected it to port A before previously, but anyway, so now I'm going to connect it to port C, and what I'm going to do with the data is I'm going to connect it to port D. The data meaning these pins, the read, write, enable, and whatnot. I'm going to connect them to the lower significant bits of port D. Okay, and then I'm going to say pin setup. This is coming from the LCD. Go to the LCD code if you're the LCD lecture if you want to know more about what I'm doing here. Okay. And then I'm going to begin by saying, well, I have 16 and I have LCD under 5 x8 dots. Okay, this way, if I compile this, you're going to see that my LCD, now it's showing all these gibberish because there's no code in the microcontroller. Okay, but now what I did, because I initialized it correctly, it actually removed all the gibberish in here. Okay, all right, so let me just do that here. I think it's easier so that we could see it. Okay. All right, so okay, so we have the pin, the LCD is already set up now, and let's get started with the configuration of the ADC. Okay, so we're going to configure the ADC, and let's do that one by one. So configuring the ADC, what does it mean? Well, we need to configure what analog pins, what is the voltage reference, and the digital I/O. Okay, what I'm referring to is the following. I'm referring to AD here. So I'm referring to this particular table. I need to tell it which one is analog, which one is input, whether I want the reference to be internal or external. As we discussed before, we're going to consider that the references, the plus or minus, are internal. So I'm going to set this to 0 and this to 0. That means these two will be 0. And what I have is I have AN0 now is connected, and I'm going to deal with it as an analog input, and the rest will be digital. I don't care about them. You can set all of them analog. I'm not using them at all, but for now, for the sake of argument, we're going to just use that. So you're going to see me putting that particular value in here. Okay, so effectively, this is the atcon1, and what I'll be doing is, let me just do, I think if I do that here, okay. Yeah, okay. So atcon1, you probably can't see it because the video is blocking it, but well, let's do that here. Okay, let me reorganize the windows, maybe you can see it. Well, I can only do one thing. I'm only blocking the code or blocking that, so I chose to block the slides. It's fine. All right, so anyway, so we're gonna configure the analog pins. What I'm doing in here is I'm reading that table. You might not see it. It's basically I'm just putting these values. So this value is coming from setting up this correctly, and the value is basically in C. All I have to do is just say atcon1 equals 0x0e. Okay, and basically that sets it up correctly. It sets up a 0 and 1 out. The other thing I want to deal with is, yes, I set up pin AN0 to be analog, but I need to tell the microcontroller that it's an actual input. So what I'm going to do is I'm going to do to the tri-state A bits dot RA0 equals 1. Okay, so I'm just telling it RA0 is an input. I don't really have to do it since I'm deciding it, but this is actually more consistent, and according to the datasheet, you do have to do it. But if you eliminate this line, it will work fine. But anyway, just good. It's good habit. Just keep it. Okay. All right. So we figured out the analog pins. It's AN0 only. We figured out the voltage reference. We set it up to 0, 0. That's what this 0 stands for in here because I put this to 0, 0. And figure out the rest of them are digital IOs, and I did this. Okay, so we need to select the acquisition time and the conversion clock. Okay, the acquisition time and the conversion clock again are here. I'll be choosing these because I'm operating on the 1 megahertz default value. So what you're gonna see me doing is atcon 2 bits dot ADCS. Okay, this decides. Let me just see, ADCS, yes. ADCS is actually the clock I wanted to operate with, and what I decided to do is I decided to put it at 0. This is basically just half of the frequency, the oscillator frequency, half of that 1 megahertz, which is basically half a megahertz. Okay, that's the clock that the ADC is going to operate on. The other one is 80 con 2 bits. I'm going to say that my acquisition time, I want it to be automatic, and I'll just basically use 1. And 1, you can see the slides, 1 is just 2 T80. Okay, so my wait time, or the acquisition, the time between I actually do the conversion and between listening to the analog input and charging that capacitor and actually doing the conversion, is going to be the same amount of time that it'll take to convert 2 bits, and that should be enough in our case. All right, and then what I'm going to do is I'm going to say, well, let's do the justification. I'm just going to basically make it right justified. So I will be using right justification here. So the lower byte is what I'm going to see. I don't like that. I need you to see these slides. So let me just do one more time. Well, it might be better, a little bit better now. But anyway, we're going to do right justification. That means it's the address L. It's going to be basically the lower significant bits are going to be here, and I'm going to just use the 2 bits in here. All right, so I did the acquisition time. I actually did the conversion clock, the input channel. Let me just see. Yes, I did the acquisition time and the conversion clock and the justification actually. So I did, let me just do that here. I did use that, so I put both of them here. So I selected which acquisition time, this is here, or this one is the acquisition time, and I did the conversion clock, and I also did the justification. It doesn't say it here, but I did it, okay? All right, so now I need to select the AD input channel. And what I mean by that is, remember, I have 13 pins exposed to the outside world. I need to figure out which one it is, and I can change them again. But because we're dealing with just one of them now, all right, so yes, so we have all these 13 outside. What I need to do is I need to figure out which one I'm converting. And again, I can change them on the flight in software. And we can see, we're going to see it later when we're dealing with more than one. I'm going to have to change that. But anyway, for now, for simplicity, we're just going to basically say, all right, the way we can convert this is by selecting the CHS. And the CHS is actually, we can go back in here. This particular table here tells me the CHS is here actually. It's in 8con0. Okay, so 8con0 dot or bits dot. It turns out to be that I have CHS is available to me, and I can just do that here. But I need to figure out what number is my AN0. So I have to go back in here and just figure out what the value is. And the value for channel AN0 is just 0. Okay, so we're going to do the 0. 0, this is decimal, by the way, so I'm just converting these to decimal, and I can do that. No problem. Okay, so that's good. So the next step for me is to turn on the module, or to turn it on, not necessarily to start sampling, but just to turn it on. And probably by default is on. I don't actually know if it's by default on or not, but I don't care. I'm going to turn it on. So all I need to do is just basically that little bit in here. I'm going to say AD con 0 bits dot AD on equals 1. And this way I turned on the analog to digital module. So I set it up now. I figured out what analog pins I need, what is the voltage reference, I figured out the acquisition time, the conversion clock, what justification I want to use in terms of the final results, and I figured out what channel I'm actually sampling, and it's going to be fixed for this example. It's going to fixed on AN0, and I turned it on. Now we go into configuring the AD interrupt if I choose to or not. All right, so yeah, so you can configure the interrupt if desired, meaning if you want to use interrupt with the ADC. As a first example, let's just not use the interrupt. We're going to use polled IO. Well, it's not an IO, but we're going to use polling to actually do that. All right. So this is for step number 2. For step number 3, wait for the required acquisition time. This is related to if you want to do this acquisition time instead of automatically computing it based on T80 or something. We're just going to skip it for now because we're doing things automatically. Now we're going to have to start the conversion, set it to go or done. Okay, and because we're going to be doing this multiple times, what I'm going to do is I'm going to choose to actually do these inside the while loop, because I'll be continuously converting values. Because if you do it once, well, this go. Okay, so this go, what it will do is it will do the, this go, wait a minute, okay, let's do that. Yes, so what happens is this particular go, I lost my train of thought, sorry. For start the conversion, set go, it turns out that you basically hit go, it's as if you're telling it, hey converter, please convert the next analog value for me, or analog value. and it will do it. And once it's done, it's just gonna stop. The ADC is gonna tell you, hey, this is the result. So as long as you need it, you need to continuously ask it to do this. So what we're gonna be doing is we're gonna put the following inside the while loop, the infinite while loop, because we will be continuously doing that. Okay. All right, so we're going to do that, and it's as simple as saying, okay, conversion basically by the go done. It's in the same register, which is ADC, AD converter or AD configuration 0 bits dot add not add on. It's actually go, and you can see that this particular this particular implementation of the XE8 has different, or the header actually, it's the header. It allows me to use them. They're all equivalent. Okay, but because for readability purposes, we're just going to say go. It's as if I'm telling it, hey, go, and start reading. And it will basically start converting. And that's it. So now it's started to convert. Now, if I do this and I stop, nothing's happening because I'm not going to see anything happening. And the reason why is because I'm not displaying it or anything. But before I do, I need to go to step 5. So step 5 tells me wait for the ADC conversion to be completed. Okay, so if I'm doing polling, so let me do this. If I'm doing polling, I need to figure out. So whenever you set the go, it will go and convert it. You set it to 1. Once it finishes converting, as you can see here in this register, it will be done. And done is actually a bar, so it's going to be 0. So you're going to tell it convert. It's going to go do the conversion. It takes some time. And once it's done, it's just going to lower that bit. So I can do it a couple of ways. It's either I'm doing it with interrupt, which I'm not doing right now, but I'm doing it with a poll IO. So what I'm going to do is I'm going to need to poll this. It's exactly the same as polling an external pin. But now instead of polling an external pin, I'm polling the status, well, let's call it status pin. And it's as simple as saying, okay, while the ADC converter 0 bits dot go, and I'm just gonna say not done. Okay, but they're all exactly the same, but I'm saying as long as this go, or you can just keep it as go, it's up to you. It's all the same meaning. If you say as long as it's go, that means as long as it's 1, that means it's still converting. Just do while loop. And I, frankly speaking, don't need to do anything. I'm just gonna do it like, hey, spin your wheels, and once it's done, you're gonna go to the next instruction. The next instruction is basically to read the ADC results that I have. Okay, so here, because I'm using poll.io, what I'm doing is I'm gonna tell it, hey, go convert, and then I'm gonna wait for it to convert. Once it converts and finishes, it's gonna be done, and done sets that particular pin to 0. And at that particular moment, I know that I have a value that is a valid, and it's stored in these address H and address L. It's not address, it's AD, resol, whatever it's like the shortcut for, but it's these 2 bits. And because it is left, I actually did it right justification. The way we're gonna do it is by saying, okay, technically, I need to organize them. They're 2 8-bit registers, so I need to put them in some sort of an 16-bit, and an integer in this particular implementation of the XE8 is a signed integer. Okay, it's a 16-bit, it's assigned, and a 16-bit, you can use whatever it is, but if you read the guide for the compiler here, it tells me the int is 16-bit. So I'm going to store these 2 things inside it. So in order for me to do this, I'm going to say, well, num equals, and I'm going to say addresh, and I'm going to shift it by 8 bits. This way, what I did is I took the address H, okay, and I shifted it by 8 bits. So I'm going to have the higher, most significant bits are going to be the same value, which I want here. Okay, so let me show you what I'm doing here on the graph. So what I did is I basically stored the address high, all of it here basically. I'm trying to store this particular address, well, I'm going to call it address high, it's not address. Okay, it's the ADC result in high and result low. Okay, the high byte is going to be here and the low byte is going to be here. I'm just trying, this command is just shifting the high into the upper most 8 bits of integer num. Okay, and what I'm going to do is I will OR it with the addres low, and this actually takes care of it. It's as if like I did exactly that, right? So it's just basic C. All right, so now I know that my number contains that value. All I can now do whatever I want with it. Multiply it, divide it, subtract it, control something else with it. I know now I convert it to a number. What I'm going to do is, for the sake of just simplicity, I'll just basically put it on the LCD that I have in here, and it's as simple as saying print int num that way. Okay. All right, so if I print num, I can basically just compile it. I'll have an error. You're gonna see it shortly, but you're gonna see now. All right, so the error is because it's like whatever it's reading, it continues because it writes a number and then goes to the cursor is moving to the next place and the cursor is next. So what I need to do is I need to clear it every single time I do it. Okay, so we're gonna clear it. So we're gonna do clear in here. Okay, so we're gonna compile that here, and let's see it. And okay, well, everything is gone, and apparently it spends more time in the clear than it spends in the print. I looked it up, that I had this issue in here. I was like, where did the number disappear? And from my reading, or from my understanding, is the clear takes a little bit longer time than actually printing, so it's mostly not visible. So I was like, okay, let's do a delay of, like, let's say 50 milliseconds or something. All right, so I'm gonna basically delay that display a little bit. So I'm gonna clear, display, delay for 50 milliseconds. So I'm gonna display it for 50 milliseconds. And what I have is I have this stupid flickering effect. So as it turns out, the fix is the following. The fix is, instead of using clear, what you need to do is you need to tell it, go to home. Basically, you're moving the cursor back home, okay, back to the home location, which is basically location 00, where the 3 is here. And now you print it. But if you do this, they will create some sort of an issue. If you have a number that is basically 36 and you have that 6, basically, let me show you what the issue is instead of me just talking about it. Okay, so what I'm gonna do here is I'm gonna okay, we're downloading it. It's downloading now. The flickering has disappeared, and I have the number 366. However, if I go down, all the way down, actually the opposite direction, you're gonna see that I'm not going to 0, and it's actually, frankly speaking, it's actually 9. The 0, 2 have been from the previous value that actually, or the latest value that was there. So what the solution is, after you go home, I'm gonna print the number, and then I'm gonna keep printing a bunch of empty spaces in here. Okay, what they will do is they will overwrite a previous value, kind of like the 0, 2. I'm just basically replacing them with spaces. It's just a hack. Okay, so what I'm doing is I'm moving the cursor every single time I'm printing. I'm moving the cursor back to the original location. I'm writing the number. This particular number here happened to be in the 9. Okay, and after that 9, I'm writing a bunch of spaces to overwrite the older value. And this way, I will actually have solved the flickering problem, and I have solved this. All right. So let's see this. Yes, I did get the 9 now. So now let me just explain to you what's happening. So now we know how to write that code, and we can see the value. What I'm really doing is the following. This particular potentiometer, it's not connected to that resistor yet. The potentiometer is, let me show you the circuit in here. What I have is I have just a potentiometer connected to 5 volts and 0 volts or ground, and it's wipe, I think it's called. The middle pin is connected to A and 0, and changing it is actually going from the maximum value of 10 bits to the lower value of 10 bits, okay? You can see it, I'm just basically moving it. It's not, like, the connection is not very good, and it's like it will change whatnot, but anyway, you get the idea. All right, so, well, these numbers are not voltage values, are they? No, they're not. What they are, they're a bunch of numbers. And as it turns out, that I basically converted it to a digital number, but I need to put a value to this digital number. In this particular case, I need to figure out, and you will have to figure out through a lab, actually, what that means. But frankly speaking, I'm effectively, if I'm converting 5 volts to the maximum number, 5 volts will be the 1024, and the 0 volt should be the number 0, because that's in the minimum number and the maximum number. And anything in between, you can actually compute it. It's not a big deal. All right? So for example, if I want to do this here, and well, why don't we compute it? We can actually compute, well, let's say 1000, or I don't need to compute it. I can figure it out. Like, for example, 500 and 256, 512, okay? Okay, 512. Well, what do you think that voltage value is? So if I'm to bring my multimeter in here and measure it, I will get 2.5 volts, because it's right in the middle in between them. So you get the idea. I'm converting these voltages to some sort of an integer numbers, and you need to, like, if you're taking these numbers and doing something with it, you need to convert it to whatever it is. In this particular case, it's voltage. I believe the lab is going to be related to voltage as well. You're going to be doing something related to voltages. If it was a temperature, you're going to move that into a different temperature. You're going to have to read the data sheet for your temperature sensor and whatnot. We're going to see it shortly with the light. You can actually convert it to 1 out. So one of you might ask, why am I not getting all the way to 0? And the answer is because I have some sort of resistances here and the connection is not good, and the ADC also has some errors as well in terms of resistances. But this is the least. For example, now I'm getting to 11. Temperature also affects it because it affects everything in here. So I got like a few minutes ago, we got the 9 as the minimum. I'm getting a 10 by pressing it like really hard. Like there you go, I pressed it, like now it's 7. So depending on like what I'm doing, but you get the idea. It goes from 0, and because I only have 10 bits, it's going to go all the way to 1024. Or, well, it didn't go to 1024, but it's close enough. I think if you convert this to a voltage, you're going to get like 4.97 or something volts, which is very, very close. All right, so this is in its basic thing, and this is using POLD.io. So what I want to do right now is I want to show you how we can do this using interrupts. So now if you look at my code in here, you're going to see that my while loop is doing a lot of the work. What if my compiler should be, or my microcontroller is doing something beside that? So what I'm going to do is for now I'm just going to let my microcontroller do just the display within the while, but I'm going to take all the ADC conversion into outside it so that it can do it in the background and then interrupts me whenever a conversion is finished. Okay, again, what I'm doing is I'm moving it, instead of polling it, always like, are you done? Are you done? Are you done? The value of the while here is I'm asking, are you done? Are you done? Are you done? Instead of me asking, I'm going to let the ADC tell me by interrupting me. So I'm going to use interrupts. Okay, so let's get started with using interrupts. So I'm going to go back in here. All right, so I'm going to go back. Some of the configurations are exactly the same. These are exactly the same because they're for the LCD. Configuring the analog pins for now, it's the same because I'm using the same pin. It's A0. The acquisition time, I'm going to keep it the same. The justification, I'm going to keep it the same. These are what these are for. Since I only have one channel now, I'm just going to keep it outside the loops. Okay, and then here I'm turning it on. That's fine. So far it's good. Okay, so we're going to stop at this particular stop here. Configure AD interrupt. So yes, now we're going to move to the interrupt. Okay, so we're going to configure to the interrupt. And how do we configure the interrupt? Like any other interrupt, you're gonna have to clear the flag. This is what interrupt flag is. You're gonna say the interrupt enable, and if you care about priorities for the ADC, let's assume you have different interrupts. Remember, we have a low priority and a high priority. You can actually select the priority bit, and then you're gonna do a global interrupt for all of them. Okay, so which registers have all of these interrupts? I'm just gonna scroll back in here. All of these are related to the interrupts, so I'm gonna do that. So what I'm going to do them is one by one, and I'm going to see that the ADIF, which is the flag, happened to be in PI. All the grayed ones, okay, I probably forgot to mention this, the gray one are not related to the ADC. They're for different peripherals. So PIR1 has like interaction with different peripherals, the TX and the SSP. It's basically for communication protocols and whatnot. Anyway, what I care about is just the ADIF. So what I'm going to do is I'm going to say PIR1 bits dot ADIF. I wanted to clear that flag, and now I'm going to set the enable, and the enable for that particular interrupt, because I'm going to enable it, PIE1 bits dot ADI enabled equals 1. Okay, and I will interrupt priority bits. If you care about the priority, whether it's 0 or 1, I'm going to just basically say bits dot ADIP. I'm going to set it to high priority. If I remember, 1 is high priority. Frankly speaking, I'm going to turn off priorities altogether, but if I remember this is the priority, I'm going to just basically set it to high priority. Next, what I'm going to do is I will set the global interrupt enable in here, and I'm going to set up this one here. This P, we didn't use it. We use it for the low priority, but this P, it's actually peripheral interrupt enable. Okay, so I'm basically allowing all the peripherals interrupts to. So not only do I need to enable the particular ADC interrupt, I also need to enable all the peripheral interrupts. So I'm going to have to do these here. Okay, so I'm going to say, well, int con bits dot peripheral enable interrupt enable or something like that. I forgot what's it short for, but we're going to do that. And then I'm going to enable all interrupts. So this is the global one. So because I don't care about priorities, you can actually turn off the priorities. I believe if, let's do the priority here. For example, if you go to rcon bits.ipn equals 0, this actually disable all the priorities, all of them. Bits, I think that's an extra G in here. That's why it doesn't like it. Okay. So this is why I set up basically the interrupt. So now it's ready to use interrupt. So instead of me continuously asking for, where is it? Here, continuously asking for the go done, I'm not gonna do that. I'm just gonna let it interrupt me whenever it finishes by writing some sort of an interrupt service routine, okay? So the interrupt service routine, let's write that here, and we're gonna write its content later, but the interrupt service routine is void underscore underscore. I have an interrupt. If you do care about priority, you would say high priority or low priority here. And what I'm gonna say is I'm gonna call it ADC sample. You can call it whatever you want, but I'm just gonna call it sample, and it's void, and I'll figure out what to put in it, okay? And I need to put that prototype in here for the sake of completion. We'll put the function prototype, and now it's good. All right. So wait for the required acquisition time. Again, we're doing it automatically. We don't have to do this. And now here's the deal here. Okay, so we're gonna start the conversion. It's gonna do the conversion, but instead of me polling it, what I'm gonna do is I'm gonna remove that here. I'm gonna tell it I'm not gonna poll its status. I'm gonna wait for the interrupt to happen. And waiting for the interrupt to happen, that means I'm gonna have to put this inside the interrupt. Okay, so we're gonna put that inside the interrupt. Okay, all right, and then here. We're gonna read it. You can either read it here or not. I'm just gonna read it inside the interrupt, and I'm gonna show you what would happen shortly. Okay. All right. So what I'm doing here is the following. I issued the go. I'm telling the ADC, hey, go, and I'm not pulling the status anymore. Whenever it's gonna go, it's gonna finish converting a single number or a single value or a single sample. It's gonna interrupt me. In the interrupt, inside the interrupt, the first thing we do usually is, again, like any other interrupt, I'm gonna make sure that the interrupt that actually called this here is the ADC, so interrupt the flag. So the flag has been raised, and the PIE1 bits dot ADIE. Yes, PIR and PIE, I think, yes. So this is the typo here. PIE. Okay, so what I did is I asked, is the flag up? Is it enabled? If it's yes, that means okay, that's correct. That's what I thought that will happen. Okay, I'm just gonna do that in here. I'm just gonna move this in here because it's a little bit more readable. Okay, I don't want my caps lock to be on. Okay, all right, good. So instead of polling now, I'm gonna wait for the ADC to interrupt with me actually. So I do this, and again, like any other interrupt, I asked, is it the ADC that called it? Is it enabled? And if the answer is yes, first thing I'm gonna do is I'm gonna say, okay, let's zero out the flag so that I don't have recursive interrupt calls. Okay, and then the next thing that you need to do is, well, you need to read that value. I'm just gonna put it in here. Okay. So now I know that it's done because it interrupted me. That means the value is stored in that ADR, like the high byte and the low byte, whatever it is. So all I have to do is write it. However, if I derive or put the variable int num in here and I just do it whenever I return, while is not going to see it. So what I need to do is I need to move that and make it, I don't like that fact, but generally in embedded systems it's okay to use global variables. It's not always okay, but we're going to do it. We're going to add the keyword volatile. And what volatile does, it does the following. It tells me that volatile, okay, this is L. Well, volatile, the purpose of volatile is because there's two places that are actually changing that number. It can be changed by the interrupt, or it can be changed by the while loop. Frankly speaking, we use volatile also by external pins. Probably I don't need volatile for this particular case, but volatile usually if you're reading a pin from outside world, the outside world might change some sort of value. The compiler or your program does not know that it has changed, so we're going to have to use volatile. Long story short, this tells the compiler, please do not optimize or do any optimization with this variable. Keep it as is. I don't want you to go and store it in certain registers and come back. It's just a directive to tell the compiler, do not optimize this particular variable. Do not hide it. Do not combine it with anything. Just keep it as is. I want it as is. Okay, so it's not going to hurt you here, but that's about it. So you're going to see that this particular number now should be fine because it's global. Everything sees it. And you can back in here and let's see if that code actually works. Okay, so I can see it. It's still working. No problem. Okay, so there's no problem. The code is still working, but now you can see that my program is free to do some other stuff now. And all I'm doing is I can basically just skip displaying it. I'm using it for the display, but I can do other things too because the conversion is being done in the background. So one might ask, why don't I just basically, instead of doing this here, why don't I just do it inside the interrupt, like whenever the interrupt does? So for example, let's do this. We're gonna call it once before, okay? Once before the while loop, I'm gonna make it basic for the initial one, and every single time you go in there, I'm gonna tell it, well, why don't you go, okay? So I'm gonna go. And the answer is like practical, actually. You're gonna see that it's, for some reason, it's very slow. Okay, because of the interrupt that happened, you see it's like here, it doesn't work as well. Well, why don't I do it that way? I think I placed it or misplaced it here. Okay, so let's do that here. I'm gonna do this and here. Okay, so it worked right now, but you're gonna see it's actually not as responsive. So I'm gonna do this. It'll take some time to convert it. Okay, I don't see it as before. It's taking some time to do it. I think it's just a little bit slower to actually turn it on from here. There's something happening, but anyway, frankly speaking, I'm just gonna put it within the while loop. I think it's a better way. So what's happening in the while loop is I'm gonna turn it on. Okay, whenever it gets off. Okay, whenever this here is done, it's at the same time it's gonna lower this to 0 and it's gonna call the interrupt. So anyway, I'm not gonna be able to do anything or set it up to 1 as long as the interrupt is happening. The interrupt goes in, takes that number, goes back in here, displays it, and the next time it turns it on again, and so forth. And that's basically what's happening. And you can see that this is exactly what's happening. So this is basically how to deal with the ADC as an interrupt or as pulled I/O. And in any case, what we care about now is that I use the potentiometer here just so that you get to explain it. But frankly speaking, what we do is we usually use instead of using a potentiometer, this actually would replace it with some sort of a sensor that changes. So my ultimate goal is to go and use that particular photoresistor here instead of the potentiometer, so I can actually do something useful. But because this particular potentiometer here, or like let's assume that I put it to 0 and it actually goes to 0, okay? Or let me explain it to you this way. Let's assume that I change this into some sort of a resistor that changes between 0 and 1, and I'm not taking the output here, but I'm taking the output outside it. So as it turns out to be that if that let's assume we'll replace it with a photoresistor. If that photoresistor its value goes to 0, you can see that I will create a short between the 5 and the 0, and it will turn off my power supply. So the solution is usually we add a little bit of a resistor in here, a tiny resistor in series with the sensor or the potentiometer. It has a certain effect, and the effect is this is voltage division. So some of the voltage is going to be dropped in R1, and this is voltage I don't need. So no matter what you do in here, you will never reach that 5 volts. You're going to reach whatever the voltage division value in here, depending on R1 and R2. Okay, so this is the equation for the voltage division for those of you that forgot about it. It's actually divide the 5 volts. Instead of having all total 5 volts being able to be dropped across the R2, you're going to see that part of it is going to be in R1 and the other part is R2. So what I'm going to do is I already connected here. I connected the 330 ohms just to show you the effect of it. I'm going to take my 5 volts from the port, like here, from the outer pin or the upper pin of the foot of the potentiometer. I'm just going to put it on top of the R1 or the 33. Okay, I can't see it. Well, all right, there you go. So the effect is the following. I will not be able to reach the 1024 because 1024 represent the 5 volts. Okay, the maximum voltage or the maximum number I'm going to get is just 1002. The same, well, I will get a little bit lower value in here. You get the idea. Why would I do this again? Because I can just remove that potentiometer, and I can just bring that I'm not changing my code. Remember, I can actually go in here and replace this potentiometer, which actually I'm changing by hand, by a photoresistor. I think something better to do is just to disconnect the power just in case. Okay, so I'm going to do that here. It is between this one here and the ground, or actually not the ground here. Let me just do that. We'll do this in series with that. Okay, let me pause, connect it, and come back. All right, so what I did here is I basically removed the potentiometer. I basically connected, you can think about these two as two resistors in series. Okay, and what I did is I took the voltage exactly at the point of connection between them. So I'm basically, what's going to the microcontroller is the voltage drop across that potentiometer, or that, not, it's not a potentiometer anymore, but it serves exactly the same purpose. It's a photoresistor. So let's do that. So we're going to do the photoresistor and I get that value. So look what I'm going to do. So the photoresistor now, if I put my finger in here, it's actually really dark. So it's actually going all the way up because it's the voltage drop is the highest. And its resistance actually changes with more light. So the more light I have, the have it. So let me just do this here. I have another light coming. So I have like some sort of a light, and you can see the more light I shine on it, it's actually the lower. So I can actually control it just with the light. And actually I can do really useful stuff with it. So for example, I can dim a light or do something a little bit smarter with it. So, and you get the idea. I'm not showing you what to do with this number now. I'm just showing you that it is changing the number. What you need to do is, instead of, for example, displaying it on the LCD, it's like, look at my code. My code in here, number have the, like the variable num has that number. You can do whatever you want with it. Okay, you can turn on something else, turn off something else and whatnot, and you get the idea. All right. Okay. So that's good. So again, I didn't do much here. I just basically connected them, and the purpose of the R1 is just in case that my sensor can go to zero ohm. If it can go to 0 ohm and I don't have that resistor in here, I will be shorting the 5 volt to the 0, and that's not good for my power supply. If, frankly speaking, for this particular photoresistor, if I go to the datasheet, which I didn't, it probably doesn't drop to 0. So I don't really need the R1 and whatnot. Of course, that would reduce my resolution because I'm using part of the resolution here. I'm never reaching 5. I'm reaching something lower. Okay, so I might be able to calculate it and use external V references as minuses and whatnot to increase resolution. But for all practical purposes, whatever I have here is fine. All right. Okay, so what I showed you right now is how to use the ADC in a polled mode, or basically keep polling the done bit, okay? And the other way is like how to use it with interrupt. Again, you can use this with many other interrupts, external, internal, or other peripheral interrupts, so you can actually do it on a low priority, high priority, exactly like any other interrupt. I just chose, because we only have one interrupt, I just chose high priority. Well, we didn't choose priorities, but it's actually vectoring to high priority here. All right. Next, what I want to do is I want to say, well, what if I have 2 inputs, okay? So what I'm going to do is I'm going to move that particular photoresistor back in here, okay? And I'm going to put the potentiometer back in here, and I'm going to tell you I have 2 analog signals that I want to be interfaced with this particular microcontroller. So I'm going to pause, connect them, and come back. All right, so what I have right now is I have a couple of analog inputs. One is going to be the potentiometer, okay, which we can see here. It's a potentiometer in series with a 330 ohm resistor, and I'm taking the voltage across the potentiometer between the middle pin and the ground, okay, and that's what I'm reading into the microcontroller into AN0. What I did is I added some very similar configuration to the what I did previously. Instead of the potentiometer, I took the photoresistor, I put it in series with 330 ohms, and I'm going to take the voltage across it, which is basically this white line, which is ground, and that one here, and I'm going to put it to AN1. And now I want my code to be able to sample both of them. Again, what I have, I'm just going to remind you what I really have here from the figure that you guys can see. I only have one ADC. So far what we did is we chose one channel, which is AN0, and it's continuously connected to that ADC. However, if I have a couple, what I need to do is I need to be multiplexing between them. So one time I'm going to convert the AN0, the other time I'm going to convert the AN1, and I substitute. Of course, the speed at which I'm sampling, it's going to be exactly half, because half of the time it's going to be dedicated to AN0 and half the time it's going to be dedicated to AN1. Again, for those of you interested in signal processing, that means I'm reducing my sampling rate by half at that point. But anyway, let's see practically what needs to be done. And I'm going to keep it with the interrupt. You get the same thing with the polled and whatnot, but I'm just going to keep it with the interrupt. So in here, what I need to do is I need to make sure that I'm using the analog pins, okay? So analog pins, well, now I'm using another analog pin, and that other analog pin is actually pin AN1. This one is here. So I need to put that particular value here. So instead of the E, I need to put, I believe, A, B, C, D, E. Okay, so it's D before the E, okay? All right, and now I'm gonna do try state A bits dot RA1 equals 1. Okay, now I'm saying that my bit A1 has to be an input too. That's effectively what I'm doing here. Okay. Okay, good. So now next what I need to do is acquisition time and the clock conversion, and well, I'm gonna keep these the same. Again, acquisition time might be like, we know the frequencies. If you care about the frequencies per channel, it's gonna be half of that. So in here, my frequency, what I'm using is half the oscillator frequency, meaning it's half a megahertz. Frankly speaking, it's half a megahertz for 2 channels. So it's going to be 0.25 for one channel and 0.25 for the other channel. So it's 250 kilohertz each. Okay, but anyway, doesn't matter for us in terms of practical purposes. It still will work. Okay, now what I have is I have an analog to digital channel select. This is where the key is. Initially, this is because I'm doing initial configuration. I'm going to tell it, okay, go to the channel number 0. Okay, channel number 0 is what's connected to AN0. So initially I'm going to tell it, well, I connected that particular one to initial to channel 0. So the potentiometer is now being sampled. Okay, now I'm going to say, hey, turn on the ADC. It turned it on, that's fine. And then we're going to configure the interrupt. That's also fine. All of that is the same. Nothing changed. What changes is in here, I'm going to say nothing changed in here. What changes is inside the interrupt. So inside the interrupt, I will basically do the same exact thing. I'm going to reset the flag. Whether I'm sampling the first one or the second one, it's the same flag. One ADC again. I don't have many of them. But now when I'm dealing with reading the ADC value, I need to figure out which value am I reading. Am I reading it for the first channel or the other channel? And the solution is as simple as testing which channel I'm currently connected to. So what I can do is I can say, well, if AD-con 0 bits dot the channel I connected is equal 0, which is channel AN0, do the following. Okay, so what I want you to do is do something, and the other option is else if AD-con 0 bits dot CHS, and it was, instead of that, it was equal channel 1, which is actually 1. I want you to do something else. So let me just write these in comments so that we don't confuse it. And I believe AD-con 0 bits. Okay, so I believe this has to be, let me just AN0, or let me just also write it as the potentiometer. I'm going to call it pot potentiometer. In here I'm going to basically say it's AN1, and this is basically the sensor. This is what I have. I have the sensor connected, basically the photo sensor here at that particular location. So all right, so let's assume that I am sampling that AN0. What I need to do is I need basically to read that number. It's in exactly the same way. I'm reading that value, but now I have a couple of numbers. So in order for me to distinguish between them, I'm going to call it number, and I'm going to call it potentiometer. Let me just go back to the global variable here, and I'm going to say this number is going to be, I'm going to have a couple of numbers, one for potentiometer and the other one is going to be for the sensor. Okay, so I'm gonna call it this one here. Maybe we call it what did I call it in my notes, so that you have the same thing, sensor. Okay, so we're gonna call it sensor. Okay, all right, so this one here, what it does, it's okay, it got interrupted, it converted everything, I zeroed out the flag, and now what I'm saying is, I'm saying, are you in channel 1 or channel 0? Sorry, if you're in channel 0, that means I'm dealing with the potentiometer. This is what I sampled. Because I sampled this, I'm gonna dump that number that I just sampled into numpot, and now I can display it or do whatever I want when I come back. However, before I move on, what I need to do is I need to change, okay, CHS. I need to change the channel so that it's actually going to AN1. So the next go around, when the ADC is going to be issued another go, which is here, it's not going to sample the same value. It's going to move to the sensor and sample it. So what I'm effectively asking it to do, okay, you sampled that, good. Give me the number. I got it. I saved it. Now what I want to do is I'm going to change the channel. So I'm going to change this channel so the thing connected to the ADC is whatever is on the photoresistor. And that's basically what's going to happen. Now I'm going to sample it. When I come back, whenever it's done, it's going to get interrupted. It's going to be here. And now what I have is number, instead of potentiometer, I have the sensor. Okay, and it's going to be exactly the same thing. I'm reading the value from the same registers. It's dumping it exactly in the same place. All right, and now next, what I'm going to say is I'm going to say, well, now the next channel has to be channel 0. Okay, you sampled me, fine. I got the number from you. Come back and do it here. And that's basically what I need to do. Of course, I need to go back to my while loop because I need to display these two numbers. So the way I'm going to display these two numbers is by displaying, well, it's the same thing. I'm just going to add a few things to make things easier for us to read. So I'm going to say print potentiometer in here. And what I'm going to do is I'm going to print, instead of the number, it's going to be the number of potentiometer, or the number that I sampled from the potentiometer. That is okay. Here it's fine. And now what I'm going to do is I'm going to set the cursor to, I'm going to move the cursor so it goes to the second row. Okay, so I want the potentiometer to be on the top row and the sensor to be on the bottom row. And I'm going to probably do the same exact thing in here. Okay, we're going to do that here. We're going to do copy, and then we're going to, I think this is cursor, and then here, but instead of potentiometer, I'm going to call it, let's call it for sensor. And then here it's going to be, instead of potentiometer, it's going to be sensor. Okay, so sensor, good. Okay, so let's try it. Hopefully it works. Okay, so I have the two numbers now. So I'm gonna move the potentiometer, and I want you to see it's actually moving the potentiometer. That's perfect. Okay, it's perfectly fine now. It's moving it, and as you can see, it's a little bit of a delay. Did I have the delay here? Okay, that's fine. So the potentiometer is actually moving. Okay, it's a little bit of, like, again, it's a little bit slower, and you get to see it now. It's jumping between numbers. It's a tiny bit slower because the time is actually split between both of them. All right. And what I want you to see is also the sensor in here. So I put that, it's actually done, and I put it here, it's done. It's both they're completely separate, and I'm doing the same exact thing. So let's do this here. So we do that just to see that the sensor is working, and the sensor, yes, it's working here, and here it's actually working, and you get to see it. So as you can see now, what I showed you right now is a couple of channels being sampled. Again, one ADC, I sample one, display it, sample the other, display it, and so forth, and I go back and forth. And of course, the sensor should change a little bit depending on the light in the room and my finger and what I'm doing here. You see, like, my finger is actually covering it a little bit. Potentiometer is probably because of the heat, and the room is getting hotter and hotter. That's why it's not going, or it's going higher, I think. All right, good. And that's pretty much it. This is what I have to say about ADCs. If you want to choose more channels, you probably, or I need to add just one more thing before I finish. So I did this, and this is kind of like, if you think about it, this is stupid. I'm doing the same exact thing, and I had to copy paste. Probably I can put these into a function and arrays, and I can organize my data. So if I have 13 channels, I can actually do it one at a time. 1, 2, 3, 4, 5, 6, and 7, and so forth. So I can do it. All right.